السلام عليكم ورحمة الله وبركاته. اليوم هذه محاضرتنا الثالثة إن شاء الله بالأنتي نيوبلاستيك agents. We will talk about drugs acting on enzymes, the anti-metabolites or anti-metabolites, or whatever you want to call them. Okay, this one is going to be part 1 from lecture 3. What do we mean by anti-metabolites? Anti-metabolites or anti-metabolites inhibit the enzymes involved in the synthesis of DNA or its nucleotide building blocks. Okay, so in previous lectures, in lecture 1 and lecture 2, we learned about drugs that attack DNA directly, either the intercalating agent or the alkylating agents or the chain cutters. All right, those go after DNA or RNA. Those go after nucleic acids directly. They also inhibit the synthesis, replication, and transcription of DNA. But these medications, they do the same work, but by inhibiting the enzymes that involved in the synthesis of DNA or RNA. Okay, so the result is the inhibition of DNA function, which is replication and transcription, or the synthesis of abnormal DNA, which at the end will lead to apoptosis. And you know what apoptosis means, which is basically cell death. And that's what we want. That's what we want in case of cancer. All right. So the first one are the dihydrofolate reductase inhibitors. Okay, the enzyme dihydrofolate reductase, and as the name implies, is an enzyme that maintains the levels of the enzyme cofactor tetrahydrofolate. Okay, so what the enzyme do? This enzyme takes folic acid, okay, and convert it to dihydrofolate, then convert dihydrofolate to tetrahydrofolate. Once tetrahydrofolate formed, is going to be converted to N5N10 methylene tetrahydrofolate, which will serve as one carbon atom carrier. Okay, it is going to carry this methylene group and add it to whatever molecule that needed. So like if we need to convert uridine to thymidine, what we're going to need? We're going to need one carbon atom, the methylene group. So that is going to serve as a cofactor. All right, this N5N10 methylene tetrahydrofolate will serve as a cofactor for the enzyme thymidylate synthase. This enzyme will convert the deoxyuridinyl monophosphate to deoxythymidine monophosphate. Okay, so as you can see from this figure, the reduction of the amount of tetrahydrofolate will lead to decrease the synthesis of deoxythymidine monophosphate, which eventually will stop the DNA synthesis and cell division, right? As you can see here also from the figure, methotrexate and other analogs inhibit the enzyme dihydrofolate reductase. We mentioned methotrexate, so it is one of the most widely used antimetabolites in cancer chemotherapy. It is very similar in structure to the natural folate. That's why it is able to act as an enzyme inhibitor for the dihydrofolate reductase. Okay, but methotrexate has a stronger binding affinity for the enzyme, and we're going to see why in just a bit. Also, methotrexate tends to accumulate in cells as a result of polyglutamylation. And why is that important? Because folate also accumulate in cells as a result of this process. And this process is an enzyme catalyzed process. It basically adds glutamyl group to the glutamyl group that is already found on the folate, or in this case, the methotrexate. Why? It's going to make the molecule bigger, larger, and it has more charge, and that will entrap or trap the folate or the methotrexate inside the cell. Okay, so that's a good thing. We have a process to increase the concentration of methotrexate inside the cells where we want it to work. But it is also a process that was used by cancer cells for resistance. So basically, some cancers decrease the level of those enzymes, the enzymes that do polyglutamylation, and they decrease the methotrexate level inside the cell. Pemetrexed and pralatrexate are both related drugs, and they were approved in 2004 and 2009 respectively, which means Pemetrexed was approved in 2004, pralatrexate was approved in 2009. Okay, it is good to mention here that leucovorin is used to rescue from methotrexate toxicity. The other name for leucovorin is what? I think you know it. It's folinic acid. Okay, we mentioned that methotrexate has stronger binding affinity for the enzyme. So why? Because methotrexate has more binding groups to the enzyme. You see, the methotrexate has the same structure as folic acid, right? The only difference is that it has one methyl group here. Folic acid has hydrogen and one amino group. The folic acid has a carbonyl. Those provide more interaction with the enzyme. So that is how methotrexate acts as a competitive inhibitor for the dihydrofolate reductase. Also, as you can see from the figure, the Pemetrexed and the pralatrexate, they are both related to methotrexate here. And on the right side, you see the folic acid, the dihydrofolate, which is basically just adding two hydrogen atoms, one here and one here. The tetrahydrofolate is basically just adding another two hydrogen atoms, one here and one there. And the N5, N10, just as the name implies, it has one methylene group between N at position number 5 and N at position number 10. All right. Okay, we talked about inhibitors of the dihydrofolate reductase, and as you saw from the previous figure, this figure, so inhibition or inhibiting the dihydrofolate reductase will lead eventually to the inhibition of the thymidylate synthase. Because if you inhibit the formation of the N5, N10 methylene tetrahydrofolate, there will be no methylene tetrahydrofolate, so the thymidylate synthase will not find the one carbon carrier to convert the deoxyuridine monophosphate to deoxythymidine monophosphate. Okay, but that's indirect. Okay, how about direct inhibitors? Okay, direct inhibitors for the thymidylate synthase are like the 5-fluorouracil. So what thymidylate synthase do? Thymidylate synthase, as the name implies, it make thymidine, just like that. Okay, and just for your information, most of the enzyme names are straightforward. Okay, so it's either named after the substrate or after the product. Okay, so thymidylate synthase will take the deoxyuridine monophosphate add one methyl group here at this position, position number 5, to make deoxythymidine monophosphate or deoxyribotymidine monophosphate. Okay, but if we have fluorine atom at this position, that will stop this reaction. How that happens? You see here, this is the mechanism of the reaction that is catalyzed by the enzyme, the thymidylate synthase. First of all, we have to mention that the 5-fluorouracil is acting as a prodrug. So basically, first it needs to be converted to the deoxyribose, defluorinated deoxyribouracil. So when the enzyme comes in, the sulfate will attack position number 4. That will open this bond and attach to the methylene group. Attaching to this methylene group will open the bond between the methylene and nitrogen number 10, which will abstract a photon, from the medium. Okay? Up until here, the reaction is going fine and nothing is happening. Okay? Because this step occurs whether it is the normal uracil or the 5-FU. 5-FU is 5-fluorouracil, okay? But after this step, okay, the uracil will lose one photon from position number 5, and that will form the bond again, and this will kick the enzyme out. Then the nitrogen will abstract this photon, form the dihydrofolate again, and this will add a methyl to the deoxyuridyl monophosphate to form the deoxythymidine monophosphate plus dihydrofolate. This is in case of the normal uracil. But if we have fluorine atom here at position number 5, the reaction will stop at this step. Okay? Why? Because it is impossible to lose F+. It's impossible to lose fluorine with a positive charge, because fluorine is highly electronegative and it will always tend to be lost as F-. It's not like that hydrogen. Hydrogen is easily lost as a proton, as H+. But fluorine will not be lost as F+. That's why the reaction will stop at this step, and that will not go forward. So the enzyme will stuck with the 5-fluorouracil, and it will not regenerate the enzyme again to redo the reaction, and this will not form the deoxythymidine monophosphate. That is why we call the 5-fluorouracil as a suicide substitute, because it's going to suicide for the cause. Okay. Other inhibitors of the thymidylate synthase, like the capecitabine, capecitabine, whatever you want to call it, is a prodrug also, but it's a prodrug for the 5-fluorouracil. As you can see from the structure here, it has the fluorine at position number 5, but it has this group attached to the amine. Okay, that will increase the lipophilicity of the molecule, which makes it easier to go inside the cell. Curious side effect of capecitabine in some patients, not in all the patients, but in some patients, is the elimination of fingerprints. That means the patients will lose their fingerprints. Why? because of mild inflammation. I think if the patient is a thief or a criminal, would like this side effect. Okay. Other inhibitor of the thymidylate synthase, we talked about the 5-fluorouracil and the capecitabine. Those inhibitors are suicide substitutes, and those act at the active site. Okay, the Ph.Ch.Lec is a folate-based thymidylate synthase inhibitors. As you can see from the structure, it looks like the folate, the folic acid. It is a little bit similar to folic acid. Okay, so this one is an inhibitor at the cofactor site. Okay, you saw the from the figure, the enzyme is attached to the uracil monophosphate, and that will come, then will attach the tetrahydrofolate. So this one inhibits the enzyme at the folate cofactor site. Okay, which makes it, by the way, more selective for the enzyme, and it has less side effect than the 5-fluorouracil. All right, we talked about the thymidylate synthase. Another enzyme which is important in DNA and RNA synthesis is the ribonucleotide reductase, which is really, it is essential for DNA synthesis. Why? Because it converts the ribonucleosides to the deoxyribonucleoside. Okay, so basically the nucleoside or the dinucleotide in this example will lose this hydroxyl group to form the deoxy. Why dinucleotide? Because it has two phosphatic groups here. Okay, so this enzyme has an iron cofactor. Okay, the iron in the enzyme will react with tyrosine residue. The iron cofactor will react with a tyrosine residue in the enzyme, which will lead to the formation of tyrosine free radical. And the job for iron not only formation of tyrosine free radical, but also stabilization of that free radical. We all know that free radicals are not unstable. Okay? They tend to react with whatever. They just want to react with anything. So iron will stabilize that. Why? They stabilize it until the ribonucleoside comes in, then the free radical will interact with the ribonucleoside and forms the deoxyribonucleoside. The hydroxycarbamide, you see the structure here, is an enzyme inhibitor for the ribonucleotide reductase. The hydroxycarbamide will interact with iron and stabilize the iron core. Basically, it will prevent iron from interacting with tyrosine. Why? Because it has lone pair of electrons here, lone pair of electrons there, also on the nitrogens. So those will make bonds with iron. Okay, this is it for this part, the first part, and we will continue with the second part in a minute. See you later.